Alright, hello everybody. So today we're talking about calculus with parametric curves. So the first thing we're going to talk about is going to be tangents, which are derivatives. Right. So suppose f and g are differentiable in the future. If I need to say differentiable, sometimes I'll just say diffable functions and we want to find the tangent line at a point on the parametric curve and it's going to go from x equals f of t to y equals g of t. Alright, so we're trying to find the tangent line at a point on the curve. So what we need to do is we'll need to use the chain rule. Okay, so let's say that we have dy by dt. Well, the chain rule says that this is the same thing as dx by dt times dt by, that's not what I meant to write, sorry. What I meant to write here is this is that's not even what I meant to write there. What I meant to write here is this is dy by dx times dx by dt, right? So kind of what you can think of is the fractions canceling out, the dx's cancel out, and you get back to what you started with. You're not supposed to cancel out these, I'm forgetting the names, but you're not supposed to cancel these out, but you can kind of just think of this as if you were canceling them out. So this is what the chain rule says. You take the derivative of y with respect to x times the derivative of x with respect to t. That's the same thing as the derivative of y with respect to t. Okay. And if we go ahead and rearrange this, then we're going to get, if we rearrange this, we're going to get dy, different color there, dy by dx, so that's the thing we're interested in. So I'm going to divide both sides by dx by dt. So if I do that, we're going to get dy by dt over dx by dt. Okay, so this is our equation right here. So if we need to figure out the derivative of y with respect to x, this is how we do it. And we can ask the question, what about the second derivative? Right, so if we want, let's say we're looking for the second derivative of y with respect to x. That's the notation we use there. And if we're looking for the second derivative, we can say that this this is the derivative with respect to x of the derivative of y with respect to x, right? Because it's the second derivative. We take the derivative of the first derivative, and if we rewrite this, we can say that this is d by dt of dy by dx divided by dx by dt. So again, we rearrange the chain rule in order to get this fraction right here, but this is how we would find the second derivative of y with respect to x whenever we're dealing with these parametric equations. And I'll say here, careful, so d squared y by d x squared is not d squared y by d x squared divided by d squared x by dt squared. So this is kind of, so if this were the equation for the first derivative, this is kind of what you would think would be the equation for the second derivative, but this is not correct, so don't use this, right? This is not correct. You have to use this formula here. You have to take the derivative of what you found here for this derivative with respect to t and divide that by the derivative of x with respect to t. And this is the way you'd actually find the second derivative. Okay. Now, the next thing to go over here before we start an example is if we say horizontal tangents, then what we mean, remember if a tangent is horizontal, then the y value shouldn't be changing. Yeah, that's what I meant to say here. Right, so if it's horizontal, then the y value is not changing, right? So the derivative of y with respect to t needs to be 0 if the tangent line is horizontal. But we know that here the derivative of x with respect to t is non-zero, right? So you just have to think for a little bit. The reason it's horizontal is because the y is not changing. And if you switched this around, let me write that here. Y is not changing, and here the x is changing because it's horizontal. And if we wrote vertical tangent, then what this means is that, well, y can change certainly, but we know that x shouldn't change if it's vertical, right? So the derivative of y with respect to t is non-zero, but the derivative of x with respect to, this was t, is 0, right? Because x should not change if it's a vertical tangent line. All right, so let's start an example here. So example 1, a parametric curve. Maybe I'll start this on the other side. Sorry. Example number 1, a parametric curve C is defined by x equals t squared and y equals t squared minus 3t. Part A is going to say show that C has two tangents at the point (3, 0) and find their equations. Okay, and the way we find their equations is going to be by using a point slope form. Okay. So we want to show that it has two tangents at this point. So specifically, let me say here, given a point xy, we need to figure out which values of t yield the x and the y, right? So we know that x is equal to 3 and y is equal to 0, but whenever that's true, we need to figure out what t is equal to. So here we know that x equals 3. So we know that we can plug in 3 for x here. So we know here that means that t squared equals 3. All right, that's just using this equation. We know x is 3, so we plug that into the equation. Now we solve for t. So t equals plus or minus root 3. Okay. And now if we plug this in for y instead, if we plug this, what's that color? We plug in y equals 0, then so we know that y is t squared minus 3t, which means that y equals t times t minus 3. And if we know that that's 0, then what that means, oh, sorry, that's not what I meant to write. Oh, sorry. Sorry, back up for a second. So we know we have the equation. Oh, sorry. That's where I messed up. The problem here is that this was supposed to be cubed. But if that's cubed, we can know that y equals t cubed minus 3t. So that means y equals t times t squared minus 3. And if we know that that's equal to 0, so we know here this is the case when y equals 0. So if we know that that's equal to 0, then either t is equal to 0 or negative root 3 or positive root 3. But notice if t is equal to 0, then that doesn't satisfy the first condition, right? Because the first condition says that t needs to be equal to negative root 3 or positive root 3. The second condition says that t needs to be one of these three things. But since 0 doesn't appear in the first condition, we can eliminate that. So we can get rid of that one. Right, now we just have negative root 3 and positive root 3 for our values of t. So I'll say here in conclusion, so both t equals root 3 and t equals negative root 3 give the point 3, 0. Okay. So now we need to compute the derivative. Computing the derivative. If we do that, then we know that dy by dx, using the equation that we wrote down, it's dy by dt divided by dx by dt. And now we just need to find both of those things, right? So the derivative of y with respect to t, we take the derivative of this with respect to t, that's 3t squared minus 3, over the derivative of x with respect to t, which is 2t. Right, so that's our derivative. And when So I'll say here, this is our first case. When t equals positive root 3, if we plug that into that equation, then dy by dx equals 3 times root 3 squared minus 3 over 2 times root 3. And that's going to be equal to, if you square root 3, you get 9. Or sorry, you get 3, but 3 times 3 is 9. So you get 9 minus 3 over 2 root 3, which is 6 over 2 root 3, which is 3 over root 3. And if you multiply both sides of this by, if you multiply both sides of this fraction by root 3, then in the denominator, you're going to get 3. And in the numerator, you're going to get 3 root 3. So 3 root 3 over 3 is just going to give you the answer of root 3. Right, so whenever you have this square root in the denominator, you can usually get it out of the denominator by multiplying both sides by the square root of 3. Then you get this, and now the 3's cancel out. So you get that. So, y equals, so we know the derivative of y with respect to x is root 3. So we know the derivative is root 3. Remember, the derivative is the slope of the tangent line, and we need to use point slope form. So y minus y0 equals m times x minus x0. Right, so that's our equation. You might have actually seen this with 1. Y minus y1 equals m times x minus x1. That's point slope form, where x1 comma y1 is the point. So this is the point here. So here y1 is the y value of this point, 0, and x1 is the x value of the point, 3. So if you plug that in, you're going to get y minus 0, which is y, equals m, slope of our tangent line, which is going to be exactly equal to the derivative. So root 3 times x minus 3. So that's the equation of the tangent line at x equals square root of 3. Okay. And now, t equals square root of 3. That's what I meant to say. So at t equals square root of 3, that's the equation of our tangent line. And when t equals negative root 3, if we just plug in negative root 3 up here, then we're going to get the dy by dx equals, so you just plug in negative root 3 into this equation, and you're going to get 6 over negative 2 root 3, which is could end up giving you negative root 3. Right, so the slope of your tangent line is now negative root 3, the point is the same. So you're going to get y equals negative root 3 times x minus 3. That's going to be the slope of your tangent line whenever t is equal to negative root 3. Okay. So that's the answer to part A. Now, part B. Let me erase this here. So at that point, we found 2 different tangent lines on the curve at that one point. Now part B is going to say, find the points on C where the tangent lines are vertical or horizontal. Okay, so first we're going to write down here where it's horizontal. Remember, if something is horizontal, then y is not changing. So we know that the derivative of y with respect to t has to be equal to 0, and the derivative of x with respect to t is the thing that's non-zero, because if it's horizontal, the y is not changing. Okay. Now, if we take the derivative of our function for y with respect to t, then we're going to get 3t squared minus 3. And we want that to be equal to 0. Okay, now you add 3 to both sides. 3t squared is 3. Then you divide each side by 3. T squared is 1. Square root each side. T equals plus or minus square root of 1. Well, square root of 1 is just 1. So t equals plus or minus 1. Okay. Now, this gives us two different options. So, at t equals positive 1, if you plug that into our functions, you're going to get a value of x and y. So if you plug in t equals 1 here, you're going to get 1 comma negative 2. And our other option is if we plug in t equals negative 1, if you plug in that into both of those two functions, you're going to get the point 1 comma 2. Right. So these 2 points give us horizontal tangent lines. Now we look for the vertical tangent lines. So we look for the vertical tangent lines, and remember that's when the derivative of x with respect to t, if it's vertical, this derivative, the x shouldn't be changing if it's vertical, so this derivative is 0. So we know the derivative of x with respect to t is going to be, so the left side of this, the derivative of x with respect to t, is 2t. That's equal to 0. So then we know that t is equal to 0. So if you plug in t equals 0 into your equations up here, you're going to get that the x value is 0 and the y value is also 0. So plugging that in up there, you get the point 0, 0. So you have 2 horizontal tangent lines at these 2 points, and you have a vertical tangent line at this point. So we're just kind of collecting information about the curve as we go. Now, part C, the last piece of information that we're going to figure out about this curve is determine where the curve is concave up and where the curve is concave down. Okay, so remember, if we want to determine if something's concave up or concave down, that's looking at its second derivative and seeing whether that's positive or negative. So the second derivative of y with respect to x, that's the thing we're trying to figure out if it's positive or negative, but we've actually got to compute what it is. So we have the equation d by dt of dy by dx over dx by dt. Okay. Now, we already figured out, and I'll write down, we already wrote that dy by dx, we solved this in part A, was equal to 3t squared minus 3 over 2t. Okay. And now we're trying to take the derivative of that fraction with respect to t. Remember, if we're taking the derivative of a fraction, we need to use the quotient rule. So if this is top function over bottom function, then the derivative of this, so the derivative of dy by dx with respect to t, using the quotient rule, is going to be the bottom function times the derivative of the top function minus the derivative of the bottom times the top over the bottom function squared. That was our formula for quotient rule. Now we just use that up here. So if we do that, we're going to get, and I encourage you to work this out, but this is going to be 2t times 6t minus 2 times 3t squared minus 3 over 4t squared, and this whole fraction is over 2t. Now, you don't have to write the parentheses with these, but I just find it's helpful to remember that it's the top function, top fraction divided by 2t. But if we write this, we can simplify the numerator, and we're going to get 6t squared plus 6 over 4t squared over 2t. That's if we simplify it. And now we can say, well, if we're dividing this by 2t, it's the same thing as just multiplying the denominators. So if we do that, we're going to get 6t squared plus 6 over 8t cubed. And now we can say, well, we can cancel out a copy of 2 in the numerator and denominator. So this is going to be equal to 3t squared plus 3 over 4t cubed. Okay, now we need to analyze both the numerator and the denominator here. So the numerator, notice, that's always positive. Right. And then if we look at the denominator, well, we know, because we're trying to figure out where this is positive and negative, remember, because we're trying to figure out whether it's concave up or concave down. We know the numerator is always positive, and the denominator changes signs. Signs change at t equals 0. Right. So we know that this fraction is going to be, well, if t is less than 0, then this whole fraction is going to be negative. And if t is greater than 0, then this whole fraction is going to be positive, right? So we know that our fraction, or sorry, our function is going to be concave up at t is greater than 0, or I should say rather than at when t is greater than 0, and it's going to be concave down when t is less than 0. So that gives us information about our curve. Our curve is going to be concave up as t is positive, and concave down if t is negative. Okay. So remember, concave up and concave down, that means the rate of increase is increasing, or the rate of change is increasing, and this means that the rate of change is decreasing, or the slope of the tangent line is increasing versus the slope of the tangent line is decreasing. Now, we want to use all of our information that we've gathered so far to sketch the curve. That's going to be part D. I'll actually erase this part here. Well, let's just remember what I wrote down on this board, that it's going to be concave up if t is positive and concave down if t is negative. Okay, so everything's going to come together in part D. The reason why we're doing all this is to sketch the curve. So from part A, so remember from part A we said that 3, 0 is a point on the curve when t equals negative root 3 and t equals root 3. And when t is equal to root 3. Now part B, said that there's a horizontal tangent line at the point 1, negative 2 when t equals 1 and also a horizontal tangent at the point 1, 2 when t equals negative 1, and also that there's a vertical tangent at the point 0, 0 when t equals 0. Okay, now we want to draw the curve, and we need some steps to draw the curve. So to draw, so we're going to need some steps. So step 1 is to plot known points. Step 2 is going to be to connect the points in chronological order from smallest t to biggest t. And step 3 is going to be to verify the curve by checking the horizontal / vertical tangents and concavity. Right, so kind of a lot there. But it says here that our first step is to plot the points. So let's do that. So this is going to be 1, 2, 3, 4, 5. This is going to be 1, 2, and 3. This is going to be 1, 2, 3. Okay, so now we can actually plot some points. So it says we need to plot them in chronological order from smallest t to biggest t. Now, notice the smallest value of t is going to be negative root 3. So this is going to be the first point that we plot. Let me use a different color. This is going to be the first point that we plot because that's at t equals negative root 3. Now our next point is at t equals negative 1. So this is our second point. Our next point is at t equals 0. So this is our third point. Our fourth point is at t equals 1. And our fifth point is back again whenever t is equal to root 3. We're going to get this point again. Right, so let's just plot all of those points in that order. So if we do that, remember we start at 3, 0. So we're going to start there. Our next point, number 2, is at 1, 2. So that's up here. Our third point is at 0, 0. Our fourth point is at 1 comma negative 2. And our fifth point is back here. So notice what we're doing. We're going from this point to this point, back to here and here, then back to where we started. So that's what we did. And remember what we said was that it's whenever t is greater than 0, it's going to be concave up. So it's going to need to keep increasing like that. Whenever t is less than 0, remember on this part of the path, it's concave down. So our function is going to have to keep decreasing like that. Remember? So this is going in this path. Remember? So this is when t equals 0. We said t equals 0, 0, 0. We said it's concave up whenever we're greater than that. So whenever we have t values after that, we're going to have an increasing function that looks like that. Whenever we have t values that are before that, we're going to have a function where the rate of change is decreasing, right? So if we go from left to right, it's going to start going down. It's going to start going down faster and faster, kind of like that. Okay, so this is actually exactly what we needed. This is exactly what our parametric curve looks like. And we can verify, as I said, also using our horizontal and vertical tangent lines. Here, this is a horizontal tangent line at this point. Here, this point, I kind of drew it poorly, but it should also have a horizontal tangent line. And this point should have a vertical tangent line. And that all matches up with what we wrote earlier. Okay. Now, the last part of this section talks about both areas and arc length. So let's move on to that part. Okay, so first we need to talk about areas. So in Calc 1, we learned that if f of x is greater than or equal to 0 for x in the interval from a to b, then the area under the curve y equals f of x between a and b, we said that the area under our function is just exactly equal to our integral of our function from a to b. Right, so that's just kind of simple. The area of our function is just the integral of the function. Now, what we're doing in this section is saying if, so that was for Calc 1, but now we're saying if a curve is traced out once by the parametric equations x equals f of t and y equals g of t, where alpha is less than or equal to t is less than or equal to beta. So these are just numbers, alpha and beta. I'm just picking numbers alpha and beta that t lies between. Then the curve the area under the curve is, so if we write our integral, so our area is the integral from a to b of y dx. Right, so that's, we said here that, so we know that y is equal to g of t. Right, we said here that y is equal to g of t. And now if you take the derivative of both sides of this, we get the dx by dt is f prime of t. And then we move the dt to the other side. So dx is f prime of t times dt. So this dx thing here is going to be f prime of t times dt. So we can just rewrite our thing in terms of t. So if we rewrite this, or sorry, our integral in terms of t. So if we rewrite our integral in terms of t, then we're going to get the integral from alpha to beta of g of t times f prime of t dt. Or the integral from beta to alpha of g of t f prime of t dt. So the reason why we have two options here is, remember, whenever we have a parametric curve, it depends which way we trace our parametric curve. Remember, for the unit circle, we can go clockwise or counterclockwise. And depending on which way our curve goes, this integral can either be positive or negative. Now, it doesn't make sense to have a negative area, so we'd say that one of these two is going to give the positive area, because this is equal to the negative of this. Right, so one of these two is going to be positive. If you end up getting a negative number, just make it positive. That'll be your answer. Okay. And I'll say here, just the difference between a and b and alpha and beta is that x is in the interval from a to b. And the difference here is that t is in the interval from alpha to beta, or the interval from beta to alpha. Right, and that's our choice that we made of which way we're following the curve. Okay. So let's do an example using this. So example number 2 is going to say, find the area under the curve, sorry, not the curve, the cycloid. Right, so this curve has a special name, it's the cycloid. So x equals theta minus sine theta, and y equals 1 minus cosine theta, and our last thing here is that 0 is less than or equal to theta is less than or equal to 2 pi. Remember, parametric equations don't have to be in t, they can be in theta or whatever other letter you want to use as well. So this time we're using theta. Now, we said here that y is going to be our g of t, and x is going to be our f of t. Or sorry, we're not using t, we're using theta. So y is g of theta, x is f of theta, meaning that f prime of theta is going to be equal to the derivative of this, which is 1 minus cosine theta. So that's f prime of theta is 1 minus cosine theta. Okay. Now, we just need to use our formula. So to find the area, our area is going to be the integral from, so we look at what t is going between. We did the same thing here. So t is going between 0 and 2 pi. And we take, using our formula, is g of theta, 1 minus cosine theta, times f prime of theta, which is 1 minus cosine theta, times d theta. Okay. Now, in order to solve this integral, we just need to multiply this thing out. So if we do that, we're going to get the integral from 0 to 2 pi of, this would be 1 minus 2 cosine theta plus cosine squared theta d theta. Okay. Notice we can't quite take the integral of cosine squared theta without using some other techniques. So what I'll do here is replace cosine squared theta using a half angle formula. Double angle formula. That's what I meant to say. So using the double angle formula, what we can replace cosine squared theta with is 1/2 of 1 plus cosine of 2 theta d theta. Right, so that's our double angle formula. The way we get rid of this is just replacing cosine squared theta with this thing here. Now, if we go ahead and distribute this 1/2, then what we're going to get is the integral from 0 to 2 pi of, this would be, so 1 plus 1/2, that's 3/2, minus 2 cosine theta, plus 1/2 of cosine 2 theta d theta. Okay. And now we just need to solve this integral using u substitution. First you solve these two integrals here, and then you do u substitution for this third term here. But just what you get out of that is going to be, if you just plug in what you get, it's going to be, sorry, I'm going to plug it in a second, but let me just write out what you get here. Alright, so you get this evaluated from 0 to 2 pi. Now you just need to plug in the numbers. So if you plug in the numbers, you're going to get 3/2 times 2 pi minus 2 times 2 times sine of 2 pi plus 1/4 times the sine of 4 pi plus 2 sine of 0 minus 1/4 sine of 0. Right, so just plugging these in is what you get. And now we can just see what goes away. Well, sine of anything times pi, any integer times pi, this is 0. So this is also 0. Sine of 0 is 0. And again, sine of 0 is 0. So all this stuff goes away, and now you're just going to get 3 pi. So your answer here is going to be 3 pi. So this would be your final answer. And if you're interested, it turns out this graph, this parametric curve is what I meant to say, actually looks like this. So it's called a cycloid because it just keeps repeating itself like this. And it just goes on infinitely in both directions like this, where the interval between 0 and 2 pi is exactly this interval. And this is the point pi, comma 2. Okay, so if you're interested, that's what the graph looks like, but your answer here is going to be 3 pi. Okay, now one last thing to talk about in this section, and that's arc length. So again, arc length is so just like area, arc length is a concept that we talked about in Calc 1, but we need to generalize that to parametric equations. Okay. So again, we're talking about arc length. So if C is a curve defined by y equals f of x, where a is less than or equal to x is less than or equal to b, then the length L of C is, so we have an equation, L is equal to the integral of, from A to B, of the square root of 1 plus dy by dx squared dx. So again, arc length is just, let's say you have some graph. I'm going to erase this in a second, but let's say you have some graph here. Starts at A, ends at B. And you have a person walking on the graph. Then the arc length of the graph is just the distance that this person walks around along this curve. So it's not just the distance from A to B, because that would just be a straight line. It's the distance on the curve from A to B. And you can imagine if you made this curve a little bit different, then this person has to walk quite a ways to get all the way from A to B, because he has to go all along this distance. So the distance on the curve we would call the arc length. And we have an equation exactly of how to find the arc length. But we want to generalize this to what we're doing here, which is parametric equations. So again, let me erase this. And we want to now learn about how we use parametric equations with this. So if C is a parametric curve described by x equals f of t, y equals g of t, and where alpha is less than or equal to t, it's less than or equal to beta, where dx by dt equals f prime of t is strictly greater than 0, then our equation is going to be L equals the integral from alpha to beta of the square root of 1 plus, well, we had a way of finding dy by dx, so plugging in our formula for that, we had dy by dt over dx by dt. Right, that was our formula for that, so that's squared times dx by dt dt. Remember, because whenever we were trying to find the integral, we had to multiply by the derivative of x. So this is going to be our equation. And now notice what we can do here. So what we can do here is try to bring in this fraction into the radical. So we try to bring this on the inside of the square root. And if we do this, then this part here is going to be equal to the square root of 1 plus dy by dt squared over dx by dt squared times dx by dt squared. Right, so now you distribute this into both of these terms. Now it cancels out here. And then once that cancels out, you're going to get square root of dx by dt squared plus dy by dt squared. So it actually simplifies this whole thing, simplifies to be this nice square root right here. And now, what we're saying here, the reason we're able to bring this inside of the square root is exactly because this thing is positive. So that's why that's important. So the fact that this is positive is why we're able to bring it inside. And now, and since dx by dt positive, we can write L equals the integral from A to B, from alpha to beta of the square root of dx by dt squared plus dy by dt squared, square root of that thing, dt. Okay, and now this is the equation that we're going to use for arc length. It's just the derivative of x with respect to t squared plus the derivative of y with respect to t squared. Take the square root of the thing and you integrate it. That gives you the arc length. Okay, now the last thing we want to do very quickly is just go through an example how to do this. So find the exact length of the curve x of t equals 2/3 t cubed and y of t equals t squared minus 2 and 0 less than or equal to t less than or equal to 3. Okay, and now we just need to use our formula in order to figure this out. So L equals the integral. It's going from 0 to 3 of the square root of, so now we know it's going to be the derivative of x squared plus the derivative of y squared dt. Okay. So it's the integral from 0 to 3 of the square root of, now we take the derivative of x with respect to t. It's the derivative of t cubed, that's 3t squared. So the 3 divided by 3, that cancels out, so you get 2t squared. Right, because 3t squared times 2/3, that's what you get. And plus, now the derivative of this would be just 2t, and then you square it, so, 2t parentheses squared. Oh, no. Your answer for the derivative was 2t squared, and then you square that. That's what I meant to say. And now you take the derivative of y, that's 2t, and then you square that. And then you got dt there. Okay. So now we just need to square these. So if we do that, we get the integral from 0 to 3 of the square root of 4t to the 4th plus 4t squared dt. And now we try to factor. So if we factor, we're going to get the integral from 0 to 3 of the square root of, here we can factor out 4t squared. Okay. And now we can break this up into 2 square roots. So now the square root of the left side, 4t squared, is going to be 2t times the square root of the right side, which is the t squared plus 1. Okay. And now it's not obvious how you would take the square root. So whenever it's not obvious how to solve an integral, the first thing we always try is u substitution. So we try our u substitution here. So if we do our u substitution, setting u to be equal to the thing inside of the square root, we're going to have the integral from u equals 1 to u equals 10 of u to the 1/2 du. Now if you take this integral, you're going to get 2/3 times u to the power of 3/2 evaluated from u equals 1 to u equals 10. And now you just plug in your numbers, and you're going to get 2/3 times 10 to the power of 3/2 minus 1. And this would be your answer. So this is the length of the curve defined by these equations between t equals 0 and t equals 3.